Hi there, welcome to another video on math problem solving. This is Bharat Divyang. So this is the puzzle for this week. It's from DMAT, from Kiran, who observed these wonderful patterns across the world. So this apparently is on the Lok Sabha wall. So here's the question. We have the red cross. If you break it down into unit squares, that's like 5 unit squares, which is basically 1 square plus 2 square. The pattern on the Lok Sabha is a little larger, probably the next level to this, which is actually 13 blocks, 2 square plus 3 square. So the question here is, can you make the next bigger pattern and prove that the number of unit squares needed is always the sum of two consecutive squares? If you'd love to solve this puzzle, please pause it here, take your time, think about it, and take a paper and pencil and actually draw these patterns. Do the productive struggle, and that's how you will learn the beauty of the problem solving methods behind it. Welcome back. If you have actually done it, then this should be the pattern as it grows. So you have the red cross, you have the Lok Sabha pattern, and the next two are probably looking more like bathroom tiles. But nevertheless, that is the pattern that you'll be seeing. And now we need to prove, the task in front of us is basically to say that, okay, if I extrapolate this to n, n number of squares, then it will still be the sum of two consecutive squares. So for that, we first let's put a cardinal number like 1, 2, 3, 4. This is the pattern that keeps growing. So if you look at it, if you start from the left column and keep moving right, you realize that it has essentially 1 plus 3 plus 1, 1 plus 3 plus 5 plus 3 plus 1 in the second case for the Lok Sabha pattern, and it keeps going. So if you actually see that it kind of grows till the maximum and then it drops back to maintain the symmetry. So here itself, you kind of see the pattern that it's the sum of a certain number of odd numbers and the sum of, again, a set of odd numbers from 1, but slightly lesser than the last one. Okay, so let's keep this aside. We'll come back to this. This apparently breaks down into 2 square plus 1 square, 3 square plus 2 square. And as you can see, the sum of consecutive odd numbers is always a perfect square. That's the first step towards recognizing the pattern. Let's look at the blanks, the white squares that surround it. In the first one, there are 4 blank squares. In the second one, it's 4 times 3. And if you look at the pattern for the blank, just focusing on one corner, it's 1 plus 2. The next one will be 1 plus 2 plus 3. In the next one, it's 1 plus 2 plus 3 plus 4. There are 2 patterns here, and we want to try to solve the problem for n squares using both of this. So first, let's look at the positive one, which means let's focus only on the colored squares. And we know that if this was extrapolated to n, you would basically keep going from the left column all the way till the maximum, which would be 2n plus 1, followed by a descending order of 2n minus 1, 2n minus 3, so on and so forth, till you get back to the rightmost column, which would be 1. So the first half, if you put all of that, you aggregate all the odd numbers from 1 till 2n plus 1, that is nothing but n plus 1 whole square. And the descending one, which is excepting the last term, everything else put together, is going to be n squared. Now let's look at the other side of seeing things, which is the blank squares, which is nothing but 4 times 1 plus 2 plus 3 plus 4 plus so on till n, which is nothing but triangular numbers. The outermost square, which is the colored plus the blank square put together, is 2n plus 1 whole square. This is the maximum length, right? So this can be used to look at the entire pattern as the total number of squares is outer minus blank. The outer one is 2n plus 1 whole square. The blank is 4 times n into n plus 1 divided by 2, which is nothing but 4n square plus 4n plus 1 minus 2n square minus 2n, which is 2n square plus 2n plus 1. Separate this out, 1n square separate, n square plus 2n plus 1 can be factorized again as n plus 1 whole square. And therefore, whether you use the first method or the second method, you still come back to the same answer as the total number of colored tiles inside this is nothing but n square plus n plus 1 whole square, which is exactly what we need to prove. I hope you found this problem and the method of solving it interesting. If there are other ways in which you can solve it, please do share that in the comments. Thank you so much. I'll see you in the next video.